I'll introduce Olivia, right? Olivia is an assistant professor in computational cognitive science at Radboud University in Nijmegen in the Netherlands. Right, she has, I mean, her expertise is both in computer science and in psychology, and she's done a lot of amazing work on many different things, but in particular on theory and meta theory in psychology. So obviously of very high interest to us here, where we're thinking about how to model human behavior, in this case for human-robot interaction. So I think I'll just pass the word to you, Olivia, and then the floor is yours. Feel free to share the screen and start the talk.
Thank you so much for the wonderful introduction. I'm just going to see if I can pass the basic test of managing to share my screen successfully. Does this look good to everyone?
This looks
very
good.
good.
Yes.
Oh, thank you. Okay. Should I be keeping track of the chat?
Well, we can keep track of the chat.
Okay.
But if there are questions, you want me to interrupt you?
Yeah, please. And I think people should feel free to unmute themselves if they also want to just ask me anything. So yeah, thank you so much for inviting me. Today I want to talk to you about how computational modeling can force theory building, and the paper that this talk is sort of based on is with the addition in psychological science, but I've put it in brackets here because I want to emphasize that this might generalize to other fields that are also interested in human behavior and cognition without necessarily being psychology itself. Right. So just an overview of what I want to touch on today. So I want to give a little bit of an explanation as to why I think computational modeling and theoretical sort of development are important, and why I'm giving this talk today, why I wrote that paper with my wonderful co-author, Andrea Martin. Then I want to go into explaining something that we call pizza problems, which I'm going to describe, but essentially it is what could happen if we don't computationally explore our theories, if we don't look in detail and specifically computationally, formally and computationally, further to just formally, but explicitly executing them as code. What could happen to our theories if we don't do that, using a toy example. And then I want to touch on a sort of descriptive model or framework, high-level description of maybe how science is done when we want to explicitly incorporate computational modeling and theorizing, again, explicitly. So I'm going to touch on this path model of science that is like a description of how we can do our science if we want to include modeling, and then sort of re-emphasize any take-home messages from the above, and allow a lot of time, hopefully a lot of time, for questions. But also, like I said, please feel free to interrupt me, unmute yourselves and interrupt me with any questions if I'm being unclear, or if you're interested in something. So why do I think this is important? Why did I write that paper? Why is this a research interest of mine, I guess? One of the things that sort of hits you in the face, I guess, if you're a theoretician or a computational modeler, is that at least in psychology, but I think this might be true more generally, we don't explicitly in science talk about our theories and our models. I think things are sort of changing, maybe in the recent past and the present, but it's still sort of not a mainstream thing to explicitly talk about our theorizing and our modeling, and furthermore our computational or formal modeling. And hopefully I'll explain why I think that using this figure. So this figure shows the last 50 years, so the last half of the last century, as what the most common words were within papers published in psychology. So this gives an example of what people were talking about in the last half of the last century, which I think is not that far off backwards in time, but maybe that also shows my age. But anyway, it's an example of the state of the field of psychology, and something that really hits me in the face as someone who's interested in models and theory is that we can see things like experiment popping up as a thing to be discussed, as a word, but not really words like theory or model. And this should be a little bit problematic if we're trying to do science, if we think that science is sort of grasping towards refining our understanding, which obviously is creating theories or refining theories, creating models, refining models, and so on. If they're not being discussed, then what are we kind of doing? So this is a bit troubling to me. And maybe this applies to all types, so not specifically within the field of psychology, but all types of kind of understanding human behavior and cognition. So maybe also true in human-robot interaction research, where you obviously need to understand the human side as part of what you do. Another thing that kind of causes concern is when, at least to me, is when I see things like this. So high-level descriptions of how we do our science, right? So this is a sort of cycle. And in the black ink, we have things that we do as scientists. So generate and specify hypothesis, design study, conduct study, collect data, analyze data, interpret results, publish, and so on. And in the red ink, we have things that can go wrong. So like failure to control for bias, low statistical power, poor quality control, p-hacking, publication bias, and harking, which is hypothesizing after results known, which is basically when you get your data and you sort of retroactively apply a hypothesis to make it look like that was the hypothesis that you had all along. So these are like the unethical things that you can do. But what's really shocking to me here in this high-level example of like the cycle of doing science is, again, where's theory, where's modeling? And I think this is disturbing because, like I said, the whole point of science is to further our understanding of a subject. So further our understanding of, for example, human cognition or human behavior. And if that's the case, then where is the refining, creating, updating of theories? Where is the creation of models and so on? That's obviously missing here. The experiments that we're carrying out, the studies that we're designing, the hypotheses that we are testing, and every step here is sort of subservient, or should be subservient, to refining our understanding, to creating theories, and that seems to be missing. Oh, and to further give a bit of background on sort of where I might be coming from here, is that I come from a sort of tradition of cognitive science, or I've been trained in cognitive science, which is an interdiscipline which has all these other disciplines that it takes inspiration of, or is inspired by, or feeds back into, depending on how you want to look at it, right? So psychology, philosophy, linguistics, anthropology, neuroscience, artificial intelligence, computer science. And when you come from a interdisciplinary background, or when you're inside an interdiscipline, you can sort of see which bits are more or less relevant to doing something. And I think that definitely helps for spotting that, for example, computationally modeling things can be very useful. And maybe it allows you to look at things, for example, in psychology, in the study of human behavior and cognition, in a slightly different way. But at the same time, it made me, and I'm not sure how other people feel about this who are modelers in other related areas, but it made me feel like, oh, maybe what I do is just somehow separate to mainstream experimental work, or is sort of in a parallel universe, or a non-overlapping, these things exist in non-overlapping magisteria. The answer is obviously no, but it's the kind of thoughts that occur if you don't feel that computational modeling is used to its full effect. At least that's how I was thinking, or I was questioning what was really going on. And to presage what I'm going to talk about in a couple of minutes, it inspired me to start thinking of things in a slightly different way. But before we get there, I just want to shift gears slightly and talk about a toy example that might help explain why computational modeling might be extremely important. So what feels like a really long time ago, given the pandemic, I tweeted why we need computational modeling. Even if everybody agrees what the area of a circle is defined as, there are apparently people unwilling to execute the formal model itself. And not only that, but the results are counterintuitive. And this is a comment on this article, which you definitely don't need to read. The preview is enough. It says, an 18-inch pizza has more pizza than two 12-inch pizzas. And the end of this sentence is, and people are losing their mind. And below that, it says, math is important, people. So I think this is a very simple, maybe even silly toy example, but it highlights something, which is that people can use sort of an informal and a formal model or a pseudo-formal model and actually get themselves into trouble if they don't fully formalize it, specify it, and even computationally implement it. And yes, of course, this is a toy example, but if we try to apply what I'm sort of proposing is needed in order to refine and build our theories, then we can do something like this. So we can create a specification which here is obviously really simple because it's just the area of a circle. So 2 times the area of these circles, which is the two 12-inch pizzas, 1 times the area of this circle, which is representing the 18-inch pizza. And we can see easily that one pizza, this very specific case, has more surface area, is more food, if we want to define food that way, than the two 12-inch pizzas. And this formal specification in maths can allow us to then create an implementation. So a programmatic executable version of that. In this case, this is a toy example, so it's very simple. So we have a function that defines the amount of food, which is exactly derived from the specification in maths that we gave. So it just computes the surface area for every circle, which represents the pizzas, and then we can have the 2 pizzas, 2 12-inch pizzas, and 1 18-inch pizza. Because we've implemented this in code, we can really simply not even bother doing anything further ourselves and just ask our model to compute for us if 2 pizzas are more than 1 pizza. And in this case, it will say false. And part of the sort of process of computational modeling, of computationally refining our theories, specifying them, is to then go back and refine the specification further if we so wish. So here we have I mean, this is still a toy example, so this is probably overkill, but we have a formalization for the summing over the areas of the circle, and then we can have a decision rule. So we can choose the surface area sum that is biggest, and then order that if we want to maximize how much pizza we get. Of course, this is a toy example, but you can add so many more things to this specification, like caring about crust or caring about other aspects, depth of the pizza, right? Because this is being modeled as a disc here, but maybe we want to model it as a cylinder, on and on and on. But even this toy example sort of explodes in potential additions for modeling something extremely simple, which is how people compute how much food there is in a pizza order. Right. So now I want to shift back to thinking a little bit more high level. I've explained with a very simple toy example how computational modeling can facilitate even over and above just formalizing our theories. But I want to give a sort of caricature just to push back against maybe some simple intuitions that some people might have. So this is a caricature of maybe how we do science. So we see some data or whatever, collect some data, then we have our hypotheses. This is a caricature that I'm saying is basically wrong. Then we have an implementation, so the code, then a specification, maybe in maths, then a theory, which is probably in natural language, in English maybe, and then a framework, which is something that gives meaning to the words in our theory. So the word memory means something completely different based on context. If you're talking about computer hardware versus people's memory. And then another caricature, sort of the inverse caricature, is you start off with a framework, and then you have a theory, and then you have a specification, and then you have an implementation. And then you generate a hypothesis, and then you collect data, and the data sort of is the end of the story. It supervenes over everything. Both of these caricatures are wrong, but I think they help us understand maybe what's a little bit more likely to be going on, and what is maybe a little bit more nuanced, and why and where computational modeling fits in and how it helps. So my kind of descriptive high-level understanding of where computational modeling fits in is that we can have this sort of path that we can move through, and a simple sort of rule is that at any point we can move upwards and refine the step above. So if we're at specification, we can move upwards and refine our theory. So in the toy example, we went from specification, a simple maths specification, to an implementation, and then I went back up and added more things to the spec. I sort of generalized it and refined it more. And if there's any kind of expectation violation, so what was happening with the pizzas originally, people were using some kind of soft heuristic or simplistic heuristic where they were just saying 2 pizzas are obviously more than 1 pizza, which is obviously not really what they believed. So it's also not true in the example I gave, so it caused some kind of violation of their expectations. So you can't move downwards in this path unless you resolve that. So you move back up and rejig what you think. You don't really think that 2 pizzas are always more food than 1 pizza, and you can explain why. So just to give like further examples or explanations here. So frameworks, at least in cognitive science, can be things like ACTA or SOAR, which are cognitive architectures. They're sort of like, they provide you with like building blocks for creating models of the brain and behavior. But then there's also things like connectionism, which is like the framework for neural networks, or the theory behind neural networks, the very high level framework theory behind neural networks. Working memory, so the human capacity for storing within a limited time frame things that are relevant to the task at hand. That's not really a theory, but like a high level framework that then you can create theories inside of. Then we have theories, so things like prospect theory from behavioral economics is an example of that, or Riscolo-Wagner for classical conditioning, or sustain, which is a computational theory of categorization, and so on. Specification, we saw that's like maths, could be natural language, but you'd have to write a lot of stuff out to make it very clear. There's also like specification languages, so TLA, plus, and Z are examples of that. But I guess mathematics is the most commonly used one. Implementation, again, we saw an example of that. So Python, C, whatever, programming languages. This is in red because at least in the fields that I work in, these are sort of the 3 steps that are the most left implicit or the most ignored. And then from your implementation, you can sort of generate hypotheses. So you can, like we had with the example, very, very simple toy example of the pizzas, we had the code's prediction, or we asked our computational model if 2 pizzas in the specific case, so 2 12-inch pizzas, were more than 1 18-inch pizza. So an example here would be that indeed that is the case, so go and collect data. So you would hypothesize that, oh, indeed, 2 12-inch pizzas are less food than the 18-inch pizza. Let's go collect data. So let's, for example, weigh them or measure them with data. I mean, this is a toy example, but that is an example of how it would go with understanding how people try to order the most pizza per order. Right. Oh, and yeah, examples of data models are things like frequentist statistics, linear regression, ANOVA, and so on. Bayesian statistics also could model the data, and so on. And like I said, you can move upwards and downwards and cycle as needed. This is kind of a descriptive framework just to really put these things in relationship to each other, not necessarily to form some kind of prescriptive guide. Right. So as I said, I don't actually believe that computational modeling is sort of separate to the rest of the kind of science that happens in psychology, more generally in cognitive science. And I think probably also true in human-robot interaction, but you can obviously butt in and tell me. I don't think these are separate. I think these are part of the same way of understanding our object of study. It's just that maybe we need to communicate with each other better, or we need to educate our mentees more in order to understand how, for example, computational modeling can contribute to building theories, to refining our theories, and so on. So yeah, thank you very much, and please feel free to ask me any questions in the chat or over video or voice.
Hey, thank you very much for a very nice talk. Do we have any questions? And you can raise your hand if you have yet asked. There is a hand. Henrik. And Tamara. Well, wait, I have to go. Which one? Not sure who went first. So you're just
sorry,
clapping.
That was just
sorry,
clapping.
Yeah, wrong kind of the hands. I keep getting confused. But Tamara has a question. Please go ahead.
First, I have to find the unmute button. Thank you very much, Olivia, for this talk. I really enjoyed it.
Well, thank you.
I was wondering what your, I was about to say hypothesis is, but in the context of what you just said, it's probably the wrong word. But what your ideas are about why the actual computational modeling part is so kept implicit. Like, why would you think that is?
Okay. Wait, do you mean in psychology or more generally?
I mean, in the context of what you just talked about, so the cognitive sciences, I would say, but also then, I mean, my experience here is, I have been in the HRI community for a long time. And for me, it has been always a problem to position my work, because not a lot of people do what we talk about today. And so my question targets that kind of as well. Is like, what is your intuition about that? Why do you think this is so neglected almost, or so hidden?
Yeah. No, I really feel your pain. So I can't speak for HRI. So I'm going to speak for what I know, which is psychology and cognitive science, and it probably applies, but let's find out. You tell me. So my gut feeling with all of this is that I think we just aren't very good at mentoring and teaching people as a field within psychology, at least. And just to be clear, I'm actually in the AI department now. So I've sort of moved into a space where I think these kind of things are a little bit more, or a lot more mainstream and accepted. But I think in psychology, we fail at even teaching our mentees how to code in many cases, which is not, I'm not saying it is a prerequisite to computational modeling. It can be learned alongside. But at the same time, if we're failing at something more mainstream, which is just coding, right? That's a much more mainstream skill than computational modeling specifically. If we're failing at that, I think we're just failing at this kind of pedagogical thing. But I also think there's a top-down systemic issue as well, which is that a lot of this work is like, what's the right word for this? It's like both prestigious. So it's seen as like, oh, this is prestigious, and you are kind of, I don't know, the people doing stuff that none of us understand. But with that, and that's the bad side, of course, that none of us understand that's not a good thing, right? But with that comes the kind of, and we don't, if we don't understand it, then yes, we kind of respect you, but at the same time, we're not going to fund you. There's this like weird situation where I think, and also there are people, let's not forget about that, who do computational modeling in a way that obfuscates right? Instead of, so they kind of do it in a way that doesn't actually facilitate other people understanding what they've done, which I think is, those specific types of behaviors are very unfortunate and very damaging to people who want to do computational modeling and actually use it to understand, you know, whatever, a phenomenon, right? Because doing computational modeling in such a way that is opaque is, yeah, that's inherently, I don't know, it's close to, if it's not misconduct, it should be. So there's all these different problems. But yeah, I'm not sure, do any or all of these apply in your opinion to HRI?
Yeah, to a certain extent, I would say so, yes. From my experience, it has been, you're certainly right with the lack of training that is offered in the field to especially the non-engineering side of it. I think on both sides is actually a lack of what you hinted on, a training of understanding math as a language, which I think, you know, it could be so exciting if we just teach it as a language instead of a science, which is really what it is, right? It is a description of nature similar to language. So yeah, I would say so. And then what very much resonated with me is also the like, well, we don't understand you, so we listen to you and we applaud you, but then please go your own way. So that part of it I've also experienced. But, you know, at the same time, funding was actually never a problem for these kind of things. As long as you throw math in it, the science funding agencies will acknowledge that. So that was the positive side of things, right? But the actual active discussions around contributions was hard for all of the reasons you mentioned. Yeah,
yeah. Well, I'm sorry to hear that.
Oh, you know, I'm now in the position to train my own students. So I hope I'm doing a better job.
I'm sure you are, because even just awareness of this, right, is a step in the right direction. I also think one thing that I forgot to mention, or maybe I mentioned it and I forgot I mentioned it, but I feel also that yeah, a lot of people don't even understand the role of computational modeling. So if you don't even understand what it's for, then it's hard to even be inspired to want to do it, right?
Right. Yeah.
Okay, Amal, you have a question.
Yeah, thank you. So I have a follow-up question to what you mentioned about like people developing models that obfuscate. And like, so within HRI, I've seen, you know, there are almost at least two aspects to the work we do. One is like the science of like understanding the science of humans, right? But then the other aspect is the engineering of actually developing the robots. And I've often come across the sentiment that like, oh, you know, modeling is more for the science aspect. You develop the model to understand how humans work. But like when we're doing the engineering part, like we just want something that works. So let's throw all this data to a neural network and just like, you know, have it work, right? Even though that's, as you mentioned, it's a model that obfuscates. It doesn't actually point out the underlying connections. And I'd be curious if you have thoughts or, you know, how you'd respond to that about the importance of modeling and engineering as well. Like your talk talked a lot about modeling in science, but what about modeling in the engineering side?
Gosh, that's a really good question. And I'm also glad that my point about obfuscation resonated with you. About the engineering side, so I haven't done any engineering in a really long time. So my undergrad, I guess, counts, but I haven't been an undergrad for a very long time. But yeah, so okay, so I think for engineering, it could make sense to use a model that is a black box, but I think it would also be difficult to argue for a black box before then, given that you and I kind of assume it's a neural network. It would be hard to argue for that before the hype. Like the hype of the neural networks is sort of is itself sort of meta black box, right? Like it's sort of, there's so much hype that if you just throw a neural network at it, that's all great. But maybe before the hype, not even maybe, I think this is true, before the hype, it would have been very difficult to argue for using a black box method in, for the kind of use cases, like, I don't know, self-driving cars, which have a whole swathe of other problems that have nothing to do with neural networks, but using neural networks for that, probably before the neural network hype, would have been much more easily argued as being unethical. So I think a lot of the problems, because you wouldn't be able to explain what it's actually doing and why, right? Like, wouldn't it be I think it would be very strange if what's an engineered component of a car that, so like an engine. So it would be very strange if the engine of the car, you said, oh, it's a black box, right? But the thing driving it that isn't a human is allowed to be defined as a black box if it's a neural network. To me, that seems like quite an obvious change in rhetoric as a function of which bit of the car, right? And then to add to that, there's a lot of other issues with self-driving cars, of course, that have nothing to do with the fact that they might be driven by entities that on some level we don't understand why they're doing what they're doing, or where their sort of limits are, how exactly they're using the things, how exactly the neural network is using what it's been trained on. But I think so I think in the case of engineering, it can almost be seen as boiling down to actually an ethical issue if you're using models that obfuscate. But I don't know if that was the direction that you were imagining, actually.
No, that makes a lot of sense. Yeah, and just actually the way your response put it in historical context also helped a lot, because like I've been in this research field only since the hype of neural networks. So it's like I've experienced that as the standard, throw data at it. But yeah, I think the ethical aspect and the fact that this wasn't always the case in, the fields of AI and computation makes a lot of sense.
Yeah, thank you. Really good question, by the way. Thank you.
Yeah, thank you. I can add one little thing, because in one of my many previous lives, I actually worked in an R&D department of a chip manufacturer for the automotive industry in 2001, 2002. And so what Olivia said was exactly right. If you had given them a neural network back then, they would have laughed you out of the door, because you cannot demonstrate that it will function safely. Therefore, it cannot be used in any safety critical system. And that was just a credo back then. And yeah, we seem to have lost that somehow, which is fascinating and worrying at the same time. But yeah, any other questions?
I can't believe we're talking about cars and neural networks, my two least favorite things.
Yes.
I like cars though, actually.
I like cars too. I think most people like cars. Any other questions? Because if not, we're sort of at the end of the time slot for Olivia, so we can also move to our next talk. But I do want to give you a final chance to ask questions if you would like to. Going once, going twice. Now there's a hand. Gustav. Yes, please.
Sorry about that. Maybe a question for the workshop overall. I also like the point about obfuscation, and it made me, in addition to maybe black boxes and so on, it made me think of papers where maths and models are presented in a quite inaccessible way, sort of proof by intimidation type maths papers. So I just, at the same time, presenting math and models in an accessible way, it's not so easy. So I thought it's, I don't know if we have time for an answer from Olivia or not, but maybe something for others to think about as well. If there are any thoughts on how to improve as modelers and being more accessible and sort of spreading the word in a nice way in that way.
Yeah, these are all really good questions. So I think, I know this isn't what you said, but I'm going to do a little caricature. So like when people say, oh, it's not easy to, I mean, you did say not easy, but when they say like, oh, it's not easy to explain it, it's so difficult. You know, the person who wrote this book has like an undergrad in physics and a PhD in maths, and they just write this stuff, and, you know, it's not their fault, blah, blah, blah. But I think saying that something is not easy, and I know this isn't what you said, like, you're not trying to make this argument, but I feel like a lot of people do, like, just because something is not easy, it's like, yeah, it isn't easy, but at the end of the day, if you don't really try hard to do the pedagogical work, the mentoring work, and the kind of whatever other aspects that are not exactly writing down, for example, the equations, it does feel like you're contributing to a kind of elitism and a kind of like in-group, who are you talking to, like 5 other people who have exactly the same degrees as you? you know what I mean? So I think it isn't easy, but I'm not sure that we can do anything about, because like science isn't easy, communicating with other people isn't easy, sharing your screen on Zoom isn't easy. Like a lot of things in life are not easy. So I think that it's just I think it's just one of those things that it isn't easy, but there is no other choice, if you get what I'm saying. So it's like, if you want to be elitist, yeah, you can just write 10 equations per page and 5 other people will get you, and 5,000 other people will pretend to get you because you're shaming them into nodding along.
I think that's a good answer. Thanks a lot.
Thanks.
Can I add a thought to this?
Yeah, please.
I was just, one of the things that I noticed growing into the modeling world, and I don't even know if I described my work as doing human modeling before, so it's kind of one of those floating terms. But one of the things that I've learned diving deeper into this is that there are certain mechanisms and patterns that repeat. And there are certain ways, we lean from each other. We loan the idea of a model and we apply it to something else. We loan the idea from physics and we apply it to behavior.
Yeah.
Something like that.
Yeah.
And this connection is never taught. It's not even pointed out. So that is potentially something that we could improve on.
Yeah, I agree. I also think that this is this kind of conceptual work, conceptual engineering, conceptual analysis, whatever term from philosophy you want to use, which is basically what we all should be doing if we aren't already doing, right? Which is, explaining, understanding, engineering, blah, 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 all the concepts that we use, right? Because obviously the definition of memory in a specific model is the definition of memory in that specific model. It's not how Tamara uses it or Gustav uses it, right? They only will use it correctly within my model if I explain it, right? So it's kind of like all of this conceptual work that doesn't have the maths, that's pre-formal, goes uncredited quite often, and you're just supposed to like absorb it. So yeah, I completely agree. Yeah, good point.
All right, I think I'm a bit sorry actually to interrupt this really nice discussion now, but we should move on to the next part of our workshop, which are the first 2